I need to begin this lesson by stating the fact that every mathematical operation you have ever learned has an inverse, has a way of being canceled out. So some popular inverses that you have encountered along the way. For example, if I take the value x equals 5 and plug it into the cubing function, I get an output of 125. And then if I take that 125 output and plug it into the inverse operation, the inverse function for the cube would be the cube root. 125 plugs it there, gives you the 5 back. So that's a pair of inverse functions. The cube root cancels out the cube, and vice versa. The cube cancels out the cube root. Similarly, an easier operation, if I plug x equals 10 into the function f of x equals 4x, I get an output of 4 times 10, 40. Then the inverse operation for 4 times x would be x divided by 4. Multiplying by 4 is inverted by dividing by 4. So then if you take that 40 and plug it into this inverse function, 40 divided by 4 takes you back to the original 10 you started with. So another pair of inverses, mathematical operations that cancel each other out. You invert addition by using subtraction, invert multiplication by using division. Powers are inverted by taking roots. Now it's time for you to learn how to invert an exponential function. The logarithmic function is created for the purpose of being the inverse of the exponential function. See, if I take x equals 4 and plug it into the function f of x equals 3 to the x, that becomes 3 to the power 4, which is 81. So a function had to be invented so that I can now plug 81 into it, and then it give me that exponent of 4 back that we started with over here. That function is denoted as log base 3 of x. So whatever the exponential's base is, the corresponding logarithm's base that cancels it out would be log base, 3 in this case. So that's created to be the inverse of the exponential function. That was the logarithm's design purposes, to cancel out this exponential operation. So one thing you need to learn at the beginning of logarithms is to make sure you understand how to write something in exponential form in its corresponding logarithmic form, because this is probably the first time dealing with logarithms for a good many of you taking this course. So when you see an exponential expression like this, remember the base of the exponential becomes the base value on the logarithm. You just abbreviate it with the letters log, and then you write a little subscript a. That's the same as the exponential base here. Now the values x and y, over here y represents the exponent and x represents the value that you get as the output. So when I write this in log form, the x expression goes in the log argument. This parentheses expression here is what's inside the logarithm value. So you write that as log base a of x equals the exponent y. So a logarithm is defined to be an exponent, essentially. Knowing how to write between these two forms is really going to help you understand. And the fact that logarithms represent exponents, or logarithms equal exponents, is a really big solidifier for your understanding of how they work. Let me show you something that my algebra teacher told us whenever we were converting from log form to exponential form. We would write a logarithm expression like this, like log base, let's say log base 5 of 125 equals 3. And if we wanted to convert this into exponential form, so we're going into expo form. What Mrs. Aaron taught us was to start with the base number here and realize it becomes the base of your exponent in the exponential form. Okay? And then what you do is you take the base raised to that power. So you have to go from the base of the logarithm all the way to the other side of the equation to get to the actual power. And so it becomes 5 raised to the 3. And then what happens is that equals the number that's in the log argument, the 125. So whenever you're converting from log form to exponential form, you say base raised to the exponent equals 125 in sort of this like spiral diagram, and that helps you get the exponential form that corresponds to the logarithmic form. So the first few exercises I've got for you in the lesson here ask you to evaluate some logarithms by first rewriting them in their corresponding exponential form, and then whenever you're trying to evaluate one of these logarithms, what you have to kind of ask yourself is, like for example, if I'm evaluating log base a of x, I need to say, well, what exponent do I need to put on the little base a in order for it to become the value x? And for some of those you can evaluate on site. Some of them are not as obvious and you'll have to use your calculator for, and I'll show you how to do that later. But let me show you these examples of how to evaluate these logarithms. So again, log form, you pronounce this log base 4 of 64. Whenever you write a logarithm, it requires the abbreviation log. It requires some form of a base value right there written as a subscript, and you have to have parentheses around something. It's argument. So in other words, writing this makes no sense. You're taking log base 4 of nothing. You have to have something inside there. You know, simply writing log base 6 is the same thing as just writing this symbol. You don't have any argument, you don't have anything that's plugged into this logarithm. So same idea here. You wouldn't just write a square root symbol without putting some number underneath it. So, you know, log base 6 of 216, now that's something, you know, we can evaluate. Square root symbol by itself makes no sense. Square root of 25, I know what that means. I know that equals 5. So whenever you're dealing with a logarithm, the full anatomy includes the log, the base value as a subscript, and then the argument in parentheses of what you're applying the logarithm to. So let's go back and evaluate some of these logarithms by remembering that little spiral trick. I've got all these set equal to a question mark. So if I write this log statement in exponential form, including the use of the question mark, what you have to do is ask yourself, to evaluate this, you say 4 raised to what power equals 64. And see, there's that spiral diagram I just showed you. 4 raised to this equals that. So when you write this in exponential form, just look at this, and it's a little more intuitive what value of x, or what value of question mark you need there. 4 to the second power is 16, but 4 to the third power takes you to 64. So the value of question mark is 3. Now what that means is, you know, through this sequence of events, what we've done is we've evaluated log base 4 of 64 equals 3. So technically your answer is just 3 as the value of this logarithm. Okay. So same idea here. Log base 5 of 5. I'm asking myself 5 raised to what power keeps me at 5? Well, in that case, the question mark would equal just 1. So anytime you take a log of a number that's the same as the base, then that's always going to return the exponent 1. Remember, logarithms equal exponents, and in this case 1 is the exponent you would need to put on the base 5 to make it stay 5. All right. This next one, I'd write this as 7 raised to what power gives me 1 over 49. Well, I know 7 squared is 49, but to get the 1 over, you need to remember the full range of all the exponents you've worked with in the past. In order to get the reciprocal, you need a negative exponent. And in order to get the 49, you need to square. So in this case, the question mark exponent would be negative, which gives you the reciprocal, and 2, which gives you the squaring. So that means log base 7 of 1/49 equals negative 2. So don't forget your use of negative exponents and how they give you reciprocal powers of your base. Okay. Log base 3 of 1. Well, I need to raise 3 to what power to make it go to 1? Well, there's only one exponent that returns a value of 1. When your base is something other than 1, the exponent in this case is going to be 0. So anytime you take a logarithm of any base logarithm of the number 1, it will always return the value 0. Okay. Now there are 2 logarithms built into your calculator. One of them has the abbreviation LOG, and you'll probably see this one in chemistry and physics as well. Whenever you see LOG, the same abbreviation as these others, but with no visible base written at the bottom, this is understood to be the common logarithm, and the base is understood to be 10. And it corresponds to the LOG button that you see on your calculator face. So if I wrote this one in exponential form, keep in mind there's an invisible 10 there whenever you see the abbreviation log. So in exponential form, this would be 10 raised to what power gives me 100,000. Well, all those zeros make it an easy power of 10 to figure out. This would be 10 raised to the 5th power. Fourth is a 10,000. Yeah, that's right. Count the zeros. So that means log of 100,000 equals 5. Okay. Yeah, if you didn't know that trick, whenever you're dealing with, 10,000, 100,000, million, count the zeros. That tells you what power of 10. Works well with the decimal system, obviously. So you've got the LOG button on your calculator, so anything with LOG you can evaluate on the calculator. The other one that you have on your calculator is the button that says LN. Now it's a little unique. The natural logarithm is the logarithm that uses base E. So I mean, I've never seen it written as log base E like this. I've always seen it abbreviated as LN. The reason it's LN and it's pronounced natural logarithm has something to do with Latin, but it corresponds to the LN button on your calculator, which is just close to the LOG button since they're both logarithms. So if I evaluate these two on the calculator, clear out this old stuff, okay? Log of 21,750. Now that's not one that I can actually evaluate in my head. That is not an obvious power of 10. I know log base 10 of 10,000 would be 4, and log base 10 of 100,000 would be 5. This 21,000 number is somewhere between 10,000 and 100,000, so this should be 4 point something. But that's as good as I can do, just without using my calculator. So what you do is you pull up the log button, and it brings LOG up on your calculator screen, and then just type the number in its argument on the inside. Close it off, and then your calculator gives you several digits of decimal approximation for it, because this will be an irrational value, but you're prompted for a 5 decimal approximation. So according to what I got, that'll be about 4.33746, because that 6th digit is a 9, so that would make me round that last digit to the 5th place up to a 6. Then now what does this number mean? Keep in mind, whenever you evaluated a logarithm equals an exponent. This is the exponent that you would need to put on the base 10. Keep in mind the 10 is invisible here, so that means 10 raised to approximately this power should give you something close to 21,750. All right, that's exactly what a logarithm always means. A logarithm gives you an exponent for the base value that's paired with it. Evaluate natural log of 496. Now this one I can't do in my head, even like I did with the log base 10, because E is an irrational number. Natural log of 496, and again, its button's right there underneath the LOG. So you just pull it up, type in the 496, close off your argument, and to 5 decimal digits, that's about 6.20658. Okay. So about 6.20658. And again, what that means is, since the base of the natural logarithm is E, this is approximately the exponent that I would need to put on E. So E raised to the 6.20658 is approximately going to give me 496. Okay. So we'll continue on looking at logarithms now by defining what its graph looks like.